Welcome to this presentation on quantum numbers. In quantum numbers, there are a bunch of different kinds, and we're going to look at them, hopefully, look at them all in this video. And all quantum numbers are is they're sort of descriptions of different electrons within electron configurations. And we use quantum numbers to actually define electrons within the electron configurations of particular atoms. Now, a quick note on quantum numbers. If you're watching this video, you're probably planning on taking the SAT chemistry subject test, or maybe even the AP chemistry exam. And as is the case with so many of these topics which are specifically, or which are only taught for the AP or for the SAT, there's going to be a lot of memorization involved. And so unfortunately in this video, pretty much all we're going to do is we're going to say a few words about the quantum numbers, and it's just to get you to remember which ones are which and how we really use them to solve problems. And so there's not going to be too much theory. It's essentially just going to be a bunch of botany, just naming what numbers mean what and how we use them. So the first quantum number we're going to define is going to be the principal quantum number. And this is the number you should be pretty familiar with when we define electron configurations and use and say things like 4s2, 3p4, 5d7. This 4, 3, and 5, those are all principal quantum numbers. And you might remember that in a couple videos ago, principal quantum numbers, we described principal quantum numbers as relating to the size and energy of an orbital. So related to size and energy of orbital, size and energy of orbital. And so as we increase the quantum number, as the quantum number gets higher, it means electrons within that orbital are going to have more energy and are going to be farther away from the nucleus than orbitals of lower quantum numbers. N, in this case, is how we define the principal quantum number. It's the sort of abbreviation. And N is always going to be some integer. And as I just said, a higher N means higher energy, and farther from the nucleus. Farther from nucleus. So in this little series right here, it's a little complicated with the D, but in general, let's see, a 5s orbital is going to have more energy than a 4s orbital, which is going to have more energy than a 3s orbital, which is going to have more energy than a 2s orbital, etc., etc. And electrons in a 5s orbital are going to be significantly farther from the nucleus than our electrons in the 2s orbital. So again, think energy and think distance, so farther from nucleus. That's the principal quantum number, and perhaps the most important quantum number. Next up is the angular momentum quantum number. And the angular momentum quantum number is actually pretty easy to remember if you can think about it in terms of the following rule. Angular momentum quantum number is related to the size, or rather, related to the shape of an orbital, And you remember that in the orbital video, we described all s orbitals as being spheres, all p orbitals as being dumbbell-shaped, etc., etc. So each individual letter, if you will, each kind of orbital is assigned a different angular momentum quantum number. So for instance, s orbitals, all s orbitals have angular momentum quantum numbers of 0. All p orbitals have angular momentum quantum numbers of 1. Oh, I should say as well that L is the letter used to describe angular momentum. So N is used for the principal quantum number, L is used for angular momentum. So S has an angular momentum quantum number of 0, P of 1, D of 2, F of 3. And so we can do a few quick problems here. What L number does a 1s orbital have? Well, all s orbitals have an L of 0. What about a 2s? Well, that's also an s, so it has an angular momentum quantum number of 0. What about 4d? Well, all d orbitals have an L of 2. So that's fairly straightforward. So to recap, we've done principal quantum number, we've described L angular momentum quantum number, now we're describing magnetic quantum numbers. I told you there was going to be a lot of memorization in this video. So magnetic quantum numbers, these quantum numbers describe the relative spatial orientations of orbitals. So relative spatial orientations of orbitals. Relative spatial orientations. I apologize, I'm such a slow writer. Orientations of orbitals. You can kind of think about this as the number of arms the orbitals have. So, for instance, we know an s orbital is a sphere, and so it doesn't really have any arms. So you might imagine that it has an m sub l, which is the letter, the abbreviation for magnetic quantum number of 0. But formally, the maximum magnetic quantum number an electron in an orbital can have is the angular momentum quantum number, and the minimum is the negative of the angular momentum quantum number. So let me describe to you what I mean by that. So in the 3p orbital, for instance, 3p orbital has an L of 1, and so its magnetic quantum numbers, every orbital except for the s has more than one magnetic quantum number. Its magnetic quantum numbers are 1, 0, and negative 1. D, so the 4d orbital, for instance, has magnetic quantum numbers of 2, 1, 0, negative 1, negative 2. And you can kind of think about this as the 3p has 3 arms, and so each of these magnetic quantum numbers describes one of the arms. Each d has 5 arms. It can hold up to 10 electrons, 2 in each arm, and each m sub l describes one of those arms. And the way we determine this, we take L, we set that as our max, we take negative L, we make that our minimum, and then we move by integers, we just count backwards from L to negative L. So it's from L to negative L and all the whole numbers in between. Alright, that's our third, and this is our fourth and final quantum number, and this one's probably the easiest to understand. It's just called spin quantum number, or m sub s. M sub s, remember that this can get a little tricky with the m's. Magnetic quantum number is m sub l. Spin quantum number is m sub s. You can remember that because spin is s. I don't have any tricks for m sub l, unfortunately. But m sub s, and the thing you should know about spin is all elementary particles, including electrons, we can think of them as sort of spherical, even though they don't really exist like this. all elementary particles have this fundamental quality about them, which we call spin, and which is essentially intrinsic angular momentum. So all elementary particles either spin counterclockwise, or they can spin, I'll do it in a different color, or they can spin clockwise. There are only 2 options, one way or the other way, and every electron spins in some fashion. And so we assign one of 2 numbers to describe this spin. M sub s can either equal 1/2 or negative 1/2. And we'll see in a moment that within the same arm of an orbital, so every arm of an orbital can hold 2 electrons. That's why a p orbital can hold a total of 6 because it has 3 arms. A d orbital can hold a total of 10 electrons because it has 5 arms. Within an arm of an orbital, one electron has to be spin up, we say, so that's a positive 1/2. I'll write that here, spin up, and one has to be spin down, which is negative 1/2. And we'll understand the reason for that in a second. In fact, we'll do it right now. There's something called the Pauli Exclusion principle, which essentially says no 2 electrons can have the same set of quantum numbers. So every electron within an atom, or within an ion, has to have a different set of quantum numbers. To show you what I mean by that, we're actually going to go through and we're going to describe the quantum numbers for all the electrons in neon. A relatively small atom, so we should be able to do it. Let's start with the 1s level. 1s level. So at 1s, we know because the coefficient here, our n is going to be equal to 1. Our L, our angular momentum quantum number, is going to be equal to 0 because we know all s orbitals have an L of 0. Therefore, our magnetic quantum number is also going to be 0. There are going to be 2 electrons in the 1s orbital. Now remember we said that electrons can have 2 spin states. They can either be spin up or spin down. Now if both electrons were spin up in the 1s orbital, if they both looked like that, this is how we represent electrons within orbitals and diagrams like that. If they were both spin up like that, well, our m sub s values would be 1/2 and 1/2, and then the 2 electrons in the 1s orbital would have the same set of quantum numbers. Mr. Pauli tells us that that's not acceptable. So what we do is we have to have 1 spin up electron and 1 spin down electron. So that's not right. Erase all that. And we're going to give us, let's see, an m sub s of 1/2 and negative 1/2. And so we're going to fill the 1s orbital like this. 1 spin up electron and 1 spin down electron. Just for your reference, the arrows represent electron spins. So that's the 1s orbital. The 2s orbital is going to be pretty similar. We're going to have an n of 2, an L of 0, it's an s orbital, an m sub L of 0, again, because it's an s orbital, and m sub s's of 1/2 and negative 1/2. So again, they're going to be spin paired like that. The 2p orbital gets pretty interesting. So let's change colors to a nice fiery red and begin. First, let's do this arm of the p orbital. So each of these boxes represents what I've been calling an orbital arm. It's just an area which 2 electrons can inhabit. So this is one arm of the 2p orbital. Oh, let me see if I can squeeze that in there. 2p. We're going to have an n equal to 2. That's our principal quantum number. Our L is going to be equal to 1 because all p orbitals have an L, an angular momentum quantum number of 1. Our m sub L, in this case, is going to be equal to 1. That's the m sub L which defines this arm. We're just arbitrarily choosing that. And our m sub s, again, we're going to have an electron of 1/2, a spin of 1/2. But instead of adding another electron to this orbital, the next electron, which we add, isn't going to go into the same orbital, it's going to go into the next orbital. Why does that happen? Well, there's a rule, and we'll maybe write it down here, a rule called Hund's rule. Hund's rule. And Hund's rule is actually pretty complicated in its sort of real form, but all we have to know about Hund's rule is it says empty subshells are filled first. So it's favorable, the universe favors having 1 electron in each of these orbitals instead of 2 in one and 0 in the other. So if we were adding orbitals, if we were sort of creating neon and we were just sort of firing electrons in there to build that atom, they would fill like this: 1, 2, 3, 4, 5, 6. Instead of 1, 2, 3, 4, 5, 6. So that's Hund's rule. And so, for instance, if we had, instead of neon, say we had nitrogen, which has 3 electrons in its p orbital, the electron configuration would look like this. There would be 3 in each arm, and none of these electrons would have pairs, would have partners. But that's interesting, but let's, let me see, let's just fill in all the electrons here and then describe their quantum numbers. We're not actually building neon. So there's going to be a negative 1/2 there to describe this other electron. Over here, our n is still 2, our L is still 1, our m sub L to describe this subshell, this arm, is going to be 0, and we're going to have the same 1/2, negative 1/2 spin states. Finally, here, our n is going to be equal to 2, our L 1. This time our m sub L is going to be negative 1, so remember our minimum m sub L value is negative L, and we're going to have the same spin states. So that is how we this is how we describe electrons using quantum numbers. So you'll note that each electron in neon's electron configuration has its own individual set of quantum numbers, and it's this spin quantum number right here which differentiates the electrons within the same arm of the same orbital. Oops, filled first. And Hund's rule, remember, said that empty subshells are filled first. So we never have 2 in one and 0 in the other. We always add electrons to empty subshells before we pair them up. And finally, to end this video, we're just going to summarize our understanding of different quantum numbers within the first 3 principal quantum numbers. And you should probably be able to fill this chart out. You probably can fill this chart out by yourself, but I'm going to stand with you and hold your hand as we go through it in a loving way, most loving and, well, I'm just going to stop. So, where were we? principal quantum number n is equal to 1. We know that when n is equal to 1, we can only have an s orbital, and so our L is going to be equal to 0. The type of the orbital is going to be 0. Our m sub L value is going to be also 0. Because for all s orbitals, our m sub L is 0. And we only have one, what I've called here, a suborbital. And a suborbital is just a location where two electrons can reside. Remember we said that p orbitals have 3 suborbitals or 3 arms, d orbitals have 5, but we'll get there. Alright, for n equals 2, we can have one 2s orbital, that's going to have an L of 0, same thing, m sub L of 0, 1 suborbital. We can also have a p orbital, a 2p orbital. In that case, our angular momentum quantum number is going to be, whoops, not 0, it's going to be 1. We can have 3 possible m sub L values, 1, 0, or -1, and we're going to have 3 suborbitals for a total, or a maximum, of 6 electrons. For n equals 3, we can have 3s orbital, and you probably know this by heart by now, 0, 0, 1. We can have a 3p orbital, in which case, again, our m sub L values are going to be 1, 0, -1 with 3 suborbitals. We can also have a d orbital, a 3d orbital. In that case, our angular momentum quantum number is going to be 2. Our m sub L values, we can have 2, 1, 0, -1, -2. Remember going from L to -L through integer-wise or whole number-wise. And we're going to have 5 suborbitals for a maximum of 10 electrons. So to recap here briefly, we've defined 4 different quantum numbers. The principal quantum number n, the angular momentum quantum number L, magnetic quantum number m sub L, spin quantum number m sub s. And this chart here summarizes how we describe electrons within these individual orbitals. So I apologize if that video was a little less than scintillating, but I hope you understand that in some cases when you've got to take a test, memorization is just the only way. I look forward to seeing you in the next and hopefully more exciting video.